So hello, everyone. Welcome to the keynote lecture by Ismaël Castillo. So I'm sure you don't need introduction about Ismaël, but he's one of the key figures in Bayesian non-parametrics, and in particular in the study of high frequentist properties of high-dimensional Bayesian methods. And in this keynote, he's going to talk about his recent works on these Bayesian trees and versions around Bayesian trees. Ismaël, do you want to share your screens?
Sure. So hello, everyone. Let me share. Okay, can you see that? Okay. Perfect. So hello, everyone. So it's a pleasure to be here. And thank you, Judith, for the kind introduction. And first, let me thank the organizers for making this online event possible and for inviting me. And it's also a pleasure to have Judith as chair, because Judith was a very inspiring person and always very supportive since the beginning, actually, of my research, my PhD studies. So this talk is about aspects of Bayesian trees and forests. And let me first introduce my two co-authors, Veronica Rokova from University of Chicago and Thibaut Randrianarisoa, who is a PhD student with me here at Sorbonne University. In the first part, I'm going to introduce some notions about trees and forests. And maybe let's start by just saying that when one has an algorithm at hand and one wants to compare it to others, so benchmarks, natural benchmarks are always tree or forest estimators, like random forests, for instance, either frequentists or Bayesians, are really natural algorithms to consider. And those have been very popular, at least since the introduction of CART. And we have, of course, random forests, which are ensembles methods, which can be built, for instance, starting from CART, and Bayesian counterparts. So let me spend some time introducing a few of the Bayesian algorithms, at least some popular Bayesian algorithms that have been used and are very much in use today. We have Bayesian CART, Bayesian forest like BART, but maybe a first algorithm that comes to mind when there is tree as word is the Polya tree, which is a beautiful object with a lot of different special cases ranging from the Dirichlet process to to smoother probability measures with densities. And what happens in the Polya tree is that you have an infinite tree, and maybe you want to be a little bit more adaptive or more flexible, and you could, instead of having an infinite tree, have a finite tree but random, and the tree itself could adapt with using the data. And this is the idea behind, for instance, Bayesian CART. There are two famous versions, which we are going to describe in more details. And there are ensembles versions like BART. Let me also mention in density estimation, the optional Polya tree, which will come in a bit later in the talk. All right, so these slides now is about, okay, some general questions. Why do we want to use trees? Suppose we want to estimate a regression function. So in this talk, I'll mostly consider the function estimation aspect of trees, although they are also very interesting classification questions. But let's focus on regression. And what you can ask is, if you use a tree method, is it any good in terms of estimation already? And if so, in which sense, for which loss functions? What is the influence of the prior you choose on the tree? And can we do, as Bayesians would like to do, maybe to quantify uncertainty, and how can we do that? And then, of course, comes the question of how do tree or forest compare to other algorithms? Are there advantages, drawbacks? And between trees and forests, are there differences? So those are very natural questions, and in this talk, I'll try to talk about some of them and give some recent results in this direction in the understanding that has been built recently on those. Let's do a little bit of a very quick overview on theory for tree methods. In terms of frequentist, so CART or random forests, there have been a lot of interesting contributions, and most of those actually focus on the estimation aspect of inference and the quadratic risk, so L2 type loss in regression. And very recently, there have been some very nice contributions in the Bayesian literature, which I'll describe in more details in a few slides. And they also consider the quadratic risk and derive rates in up to logarithmic terms. Overall, there has been very little work yet on uncertainty quantification and confidence sets. And maybe to better to give an idea of the direction we're going to take, let's look at a picture of what we'd like to explain or provide theory for. Let's give a little picture. So here we have some data points in black, and those are noisy observations from a regression curve in green. I hope you can see it. It's a triangle type curve. And if you use a Bayesian, for instance, Bayesian CART algorithm, you will have some posterior samples, and maybe from those you can build some region. And in practice, what we do, for instance, is that we can draw a lot of posterior plots, and then we get sort of a spaghetti plot or maybe a sort of band, and then we use it to say, okay, that's a credible set, and we hope maybe it's a confidence set. That's what we do in this picture. So the truth is in green, and we have some bands. So either the red one or the gray ones are Bayesian credible bands, and it turns out that they contain the truth. So and when we plot this, note that we are talking about bands. So it means that we are making an assessment about a certain loss already, about namely the supremum-norm loss. Okay, so if we want to give a theoretical justification to this picture, we'll need to talk about supremum-norm and confidence bands, which and we cannot do that if we talk about the quadratic risk, which is also very interesting. But so at least if we want to give theoretical support to this picture, we'll need to focus on the supremum-norm. Let's introduce just some classical notation. So here, since we are in regression, the unknown object is a function. We put a prior on it, and the data is a distribution of x given f, and we can form the posterior, which is a conditional of f given x. And from the theoretical perspective, we can analyze it from the frequentist point of view by assuming there exists some an underlying truth, f naught, and we study the posterior distribution in probability under the pf naught distribution. An important concept is then the convergence rate of the posterior distribution in terms of a distance d, and it is we said that the posterior converges at rate epsilon n for d if asymptotically all posterior mass lies in a ball of radius f naught and radius epsilon n for d. Okay, so now we can describe these two very interesting recent contributions on Bayesian tree and forest posteriors. So there is a work they were almost at the same time, published slightly at different times, but so there is the work by Veronica and Stephanie van der Pas on which so where the authors prove a convergence rate in terms of a quadratic type risk, so the empirical one at the design points, and they get a near optimal rate up to log factors for alpha Hölder functions, where alpha is at most 1, and this restriction comes from the fact that you look at histograms. And then Linero and Yang considered soft versions of trees and forests, and obtained results for any alpha positive. Then you don't get histograms. You lose a little bit this simple aspect of simple estimator, but the building block is a smooth learner set. And these results, they are obtained using the general theory of Gösel-Gosch-van der Waart by checking prime mass conditions and sieve and entropy, and using the fact that the L2 distance is a nice likelihood-related distance for which testing rates are quick and exponential. And this, it is well known that since a few years, so people have tried to use these techniques with norms like the supremum-norm, but it appears to be more difficult, and then we need to use some different techniques. Okay. Let me conclude this introduction by a very informal introduction to CART and B-CART more particularly. So if you are a little bit familiar with CART, you probably know this picture, and if not, don't worry, I'm going to give more details in the next slide. And just from this picture, what you should, the message is on the left-hand side, what you get in the end from the algorithm is partitioning of your input or predictor space in regions. Here we have 3 regions, and some values, the betas, which are the values of your histogram output, so here in dimension 2. And the way the partitioning is constructed is via a tree in a recursive way. And on each branch, you put certain splits which define the way you cut your space. So already here on this picture, we see that there are 3 main ingredients: the splits, the tree, and the parameter values. And this will come in all the time in the next slides. And the B-CART or Bayesian CART, I'll say B-CART for short, is the same, but everything is random: splits, trees, and parameters. Let's see B-CART in action in dimension 1. And suppose for the splits, we split always at midpoint. So always in the middle of the interval for simplicity. So first we have to decide, do we want to cut or not? And if it's the color blue will mean that we cut. Okay, so here split at midpoint, so we decide to cut at 1/2, and then we have to on each side of 1/2 we have to further decide whether to cut or not. So here on the left we decide to further cut, and on the right we stop. So a little square in the tree, which is building up recursive on the so down in the picture, and etc. So now we have cut. So on the so going back. So here on the left we don't cut, and on the right we cut, and here we end all the cuts. Okay. So here we get a tree. And from the tree now, once we have the tree, this gives us some partition where you can see here, which is given by the blue vertical lines. And once we have this partition, it just remains to draw some heights at random to get a histogram. Okay, so the histogram is just this random histogram is just built on the random partition that has been obtained by the tree, the random tree sampled on the left-hand side. Okay, so here the only thing that's not random is the splits. We assume that we always split at midpoints. We can relax that. I'll talk about that a bit later. Okay, so that's the same in dimension 1. Just a little illustration again. You can put the values of the heights at the bottom, at the leaves, and you can do that in higher dimensions. For instance, you can put different colors within the tree corresponding to different cuts in different directions for the cut. All right, so just again to summarize, we get these ingredients: the tree, the splits, which we'll take at midpoint, and the heights, which for regression we'll take as Gaussians, although we could take something else. All right, so that's it for the introduction. Let me now give a very brief outline of the talk. In the first part, I'll focus on regression. In the second, on density estimation, and I'll conclude by discussing briefly smoothing aspects of forests. So regression, let's consider a signal plus noise model. So that can be, for instance, the Gaussian white noise, where you observe some function in a continuous time in some noise. And this is an idealized version of non-parametric regression in fixed design. And we can deal with both models, but for simplicity for the talk, let me just consider Gaussian white noise. And immediately in 2 slides, I'm going to project it, so it will just be a simple sequence model. Okay, so just to introduce some notation, let me recall the definition of the Haar basis. So on this slide, I guess you know the Haar basis, but what's important is maybe you can notice that I arranged the Haar basis in a kind of a tree fashion, and we have the scale index L will be the depth, and we have the location index K, which tells you where you are on 0, 1. And 2 important notation: ILK is the dyadic interval, and FLK is the Haar wavelet coefficient. Okay, so if you have the Haar basis, or actually any orthonormal basis, you can project the white noise model to get a sequence model. And in this setting, we'll need some regularity conditions. We can assume that we'll assume that we have signals that are that have a certain regularity, and in particular, typically we assume alpha Hölder smoothness. So if you are alpha Hölder, then you will be in the space which is denoted H alpha M with regularity alpha index. Okay, and so this inclusion is which I mentioned here is for the Haar basis. It's true only if alpha is between 0 and 1. Okay, so now let's be a bit more specific about the BART prior. I didn't tell you yet how we draw at random the trees and the heights. So the tree, so there are 2 versions of BART. We'll take for now version 1, which is you follow a certain Galton-Watson type process. Namely, you just give yourself probability of splitting at each node. And we take the probability of split to be decreasing exponentially fast with the depth in this way. So it's okay. So if you are quite down in the tree, you are less likely in the prior to split further. And for the heights, we take some Gaussian heights with a certain scaling. So here independent with a certain scaling Gn. So I'll explain a little bit more about the scaling later. Okay, so to give a first result, if you take this BART prior with the split at midpoints, then you can show that for any alpha Hölder function, the posterior contracts at rate epsilon n, which is given here, and it is the minimax rate up to a log factor for estimating alpha Hölder function. So it's near optimal. So that's great news, because you up to a log factor, you, at least in terms of estimation, you are near optimal. And before giving, so that's the first version of the result, before giving a slightly more general theorem that also includes the other BART prior popular in practice. Let me just explain a few connections, and actually that will be very important in the proof. So you see that you can, if you want to summarize the prior using a tree, you can build a tree and put the random heights at the leaves. Okay, so that's one way to explain the output of the prior. But you could also actually, and that's equivalent, as long as you here observe that I've added the root node here on the top to the tree. And if I add it, then there are the number of magenta nodes is equal to the number of blue nodes. And that just to say that there is a dictionary between these heights, which are in magenta, and what I wrote in blue is simply the R wavelet coefficients of the resulting histogram. And you can go back and forth. There is a matrix which is it's almost a change of basis matrix, except that you have this scaling. So because of this scaling is the reason why we had also to scale the variance in the heights of the Gaussians. Okay, so if you rescale here, you wouldn't have to do the scaling. Okay, and still equivalently, you get external wavelet coefficients for where you stop. So those correspond to the histogram heights, and the internal ones, those are for the wavelet coefficients. And if I give you this tree, immediately you can build this dyadic partition of the unit interval. Okay, and in terms of wavelet coefficients, the tree just tells you that everything that is outside the inner nodes has wavelet coefficients 0. All right, so now the standard Bayesian CART prior, given once you have sampled the tree, given the tree, it is you just take your histogram heights Gaussian. And you can wonder, okay, so how does it translate with this dictionary in terms of wavelet coefficients? Well, that gives you still a Gaussian, which takes a form a little bit like a G prior. So that's why we call it the wavelet G prior. And on the other hand, you can also start from a Gaussian on the inner coefficients and translate it into the histogram heights, and that gives you a different prior on the histogram heights with some matrix here of covariance. And actually, this second prior is slightly easier to study because it has a diagonal covariance matrix. So that's our first. We started actually from here, and then we could, using this equivalence, this dictionary, we could then get also the results for the true Bayesian CART. All right. So now this slightly more general statement, you can, instead of doing this Galton-Watson process with the split probabilities, you could also just sample a tree at random with a certain number of leaves. So for instance, draw at random a number of leaves, and then given this number, draw uniformly among all the trees with this number of leaves. So that's for the tree priors, and for the heights prior, you can do what I just discussed. So either you do the wavelet independent prior, the first one, or you do this G prior, which corresponds to drawing independent heights. And if you do that, you get the same result as before. Okay, so near optimal rate in sup-norm. Some comments. The prior is adaptive to the unknown regularity alpha. You didn't use alpha to build the prior, so that's nice. It gives a second example of sup-norm adaptation. For now, we only knew the spike and slab prior, studied in this very nice paper by Judith and co-authors. Here we get some tree-structured a pattern instead of having an arbitrary pattern used with the spike and slab. Right, so the tree structure is enough for catching sup-norm adaptation. And here you may wonder whether the log square is because we were not careful enough in the proofs, and it turns out it's not the case. You can show, at least with the priors we considered here, that this log factor is necessary and you have a lower bound type result for the posterior. And this is, in a sense, you can view that. That's a conjecture, but because here it's for the priors we considered, but we can conjecture that for likelihood-based methods using, for instance, BART-like trees, you lose a log factor. So this is a price to pay, or a signature for using the tree in SUPNORM instead of maybe spike and slab where the pattern is arbitrary.
So Ismaël, can I ask you a question?
Yes. Yes.
So do you mind if people interrupt you to ask questions? So, well, I suggest if you have questions, maybe you can write them on the chat.
Sure.
But I just had like a quick question for these slides. So according to you, what would be the advantage of using this sort of Bayesian CART over like a spike and slab? Is it computationally much more easy? Or?
So that's a very good question. So so there are different things. So I think that that's one of the research directions I mentioned at the end. So we anticipate already a little bit, but one possibility, actually, intuitively, the tree gives you this structure. So in a sense, if you have for instance, a computational budget of wavelet coefficients you are allowed to look at, you may, the tree may be advantageous because it is quite sparse. And you get a lot of structure, whereas if you have to look at all possible combinations, like in the spike and slab, combinatorially it grows much more quickly. So I think it's very sparsity related. So taking a tree is making some relatively strong assumption, but it could be quite favorable in high dimensions because you could take advantage of an underlying tree structure. And this occurs, for instance, if you have signals with the jumps, you have very smooth signals between the jumps. So you have the wavelet coefficients are very small, and at the jump you have some high signal, and typically this type of signals will result in a tree, in a sparsity type thing. So that's one way of answering. Okay, so now other extensions. So you can do higher dimensions, fixed dimensions. We did that in the paper using tensor wavelet basis. You can have soft tree versions. So for instance, you can take, instead of taking the hard basis, you can take a S-smooth wavelet basis. And then you get results for arbitrary smoothness, essentially, but the nice and simple histogram interpretation with heights is lost. I mean, this partitioning is lost. Okay, so another interesting series of related results is about multiscale norms and behaviors. Indeed, the SUPNORM, you can link it to, in a certain way, to you can bound it from above by some sum involving wavelet coefficients, and there is a 2 to the L over 2 here. So so essentially this is up to logs, it will converge at the same rate as the SUPNORM. So if you forget about the 2 to the L over 2 and also about the sum, so just transform it in max and sups, it turns out that you get a space in which convergence at rate 1 over square root of n is possible, as long as you don't wait still a little bit here, just accounting for the fact that the max of Gaussians of 2 to the L Gaussians is of the other square root of L. If you do that, then you can show that in multiscale norms you converge at parametric rate, which will be important in a bit later in the talk. And also let me mention a very nice recent preprint by Judith and Veronica, who considered a little bit in this vein. You can also look at the local behavior and can show that the BART is locally adaptive to to the special to possibly inhomogeneous smoothness. So here an example I took from their paper, where you have the ground truth is on the first half of the unit interval is a Brownian motion path, and then you extend it on the second half by a constant. And what you can show is, what you can see is that in blue, for instance, you have a kernel method, which with a very small bandwidth, and you see it's very wiggly. And you could also take a much larger bandwidth, but then you are too smooth in a sense. Whereas the BCART prior catches well the inhomogeneity by really being wiggly in a sense on the left hand side and being constant actually on the right hand side. Okay. Another thing I'd like to mention is about okay, here we get sup-norm results, but at the end of the day, are those sup-norm results that different? So maybe it's harder to prove technically, but in fact many priors will have the same. Well, that's not the case. So if you take maybe the simplest tree prior you can consider, so namely you take instead of having a very flexible tree as in BCART, you take a flat tree. So that would be actually just a sieve prior. So you draw at random a certain depth, and once you get this depth, you just take the whole tree up to this depth. So it's really a sieve prior. If you take this prior, the adaptation it does is good in L2. You can show that you are optimal up to logs in L2, but you are suboptimal in the sup-norm. Meaning that you have to be careful, and sup-norm adaptation is in a sense is more difficult. You need enough flexibility in the prior to be able to get it. Okay. So you can, as I mentioned before, you can do a non-dyadic BCART. We have in the paper some extension. We still have some relatively strong condition on how you need to make the cuts. So essentially this balancing condition means that when you go deeper, you need to get closer and closer to the real, really dyadic cut at mid-split. But at the beginning, in principle, you can be quite arbitrary. But it's not completely clear if you are fully flexible whether you can get really this multi-scale of sup-norm behavior. Quickly some proof ideas. So there are two elements. So here is just a bit, maybe it will look a bit hand wavering, but I just want to give a little bit of the idea of how you prove this sup-norm result. On the one hand, you want that you don't want your posterior to select too deep trees. So you want, so if you have a tree that goes further down regarding to the standard cutoff, the optimal cutoff for the given regularity alpha you are considering, you don't want the tree to have many leaves here down there. So you can, the first step is to prove that the posterior puts much less mass on those deep trees than it does on the trees which cut earlier. And the second part is, on the contrary, if you miss some large signal node, so it must be before above the cutoff, then your tree T has a much less posterior mass compared to T plus, where T plus is just the tree that you get when the smallest tree that you can get by including the nodes up to the signal you missed. All right, so there is a kind of recursive flavor in this type of proof, which kind of matches well the recursive nature of the trees. So now I'll discuss briefly confidence bands. One way, that's one way to go, at least one, I'll describe one construction for which we can get frequentist coverage. To do so, we need a center for the confidence band and the radius. and the center. So you could take in principle any aspect of the posterior, like posterior mean, but here we chose to take what we call the median tree, and it is what is a median tree? It's a set of nodes, so the set of pairs LK, such that the posterior probability of inclusion of the node LK is at least 1/2. And I wrote definition here, but it's more a lemma, so you can check that this is indeed a tree. And okay, so let's denote it. This denote its depth by d star, so the maximum depth of all the nodes in it. You can define a median tree estimator just by taking so here in the white noise model, you just take xlk over each node inside the median tree and 0 outside. And then you can use the depth of this median tree to define a radius, which will essentially give you the correct rate here. And if you want, so if you know a little bit about this confidence band and adaptive confidence bands result from the frequentist literature, it's known that in the supremum it's impossible to have such bands in all generality, but you can if you assume some self-similarity type condition. And essentially, this condition means that you at each level, so kj of f here is the wavelet projection up to level j. You need at each level to have roughly the same type of signal strength. And if you assume so, you can the band which is centered at the median tree and with radius sigma n as defined above has frequentish coverage going to 1. It's a bit conservative. Credibility going to 1, so it's credible set, and it has the right diameter in the minimax sense up to log factors. So this Vn has to be larger than square root of log n. All right, so now let me briefly refine. You can refine a little bit this construction by intersecting this set with something else. And the possible way to do so, so remember before I mentioned that in the multiscale norm, you could get the parametric rate, and you can even get more than that. You can get a limiting result, Bernstein-von Mises type result. I'll come back to that in a few slides. By doing so, it enables you so as implication, it will get you that if you take a credible set in this multiscale space, it will also be a confidence set. So this ball of radius, essentially constant over square root n, asymptotically, it will also be a confidence set. So that implies that the Cn set, which is here, this intersection set not only has, unlike only the first part, which has coverage going to 1, here it has coverage going to 1 to a given fixed 1 minus gamma coverage. So it's a bit less conservative, and it corresponds to the gray area here in the earlier picture. Okay, so that's it for regression. And now let me switch to density estimation. So what can we do in density estimation? You cannot really use the B-CART prior anymore because the histogram can take negative values, for instance. So one first idea would be to say, okay, let's take the B-CART prior and let's renormalize it or put it in exponential and renormalize it so that we have a random density. So that would be a possibility. But say a more canonical idea is to use or to start at least from a Polya tree prior, because we know that the Polya tree is kind of canonical in density estimation. It has many nice properties, conjugate in particular. And we are going to give it even more flexibility by, instead of taking the infinite tree, by picking the tree inside the Polya tree at random. Okay, so let me briefly recall the Polya tree construction. So using the same notation as before for dyadic intervals. So for instance, here I10 is just 1/2 3/4. The Polya tree prior, it just attributes a random mass to any of these dyadic intervals by a certain product of beta random variables along the tree. So the tree is indexed by the random variables, and they on each here, if you have two branches that go down, the sum is 1 to conserve the mass. And the idea of the Polya tree is that these variables y, they model the conditional probabilities. Given that you are in a certain dyadic interval I epsilon, what's the probability that you that you are on the interval on the left? And under center conditions on the parameters of these beta variables, you have almost surely a density. All right. Okay, so that's the classical Polya tree, but we could do the same as we did before, just cut the infinite tree using a random tree. So what we can do is sample the tree at magenta tree here at random, for instance, using the Galton-Watson type prior. And then given this tree, just sample the resulting histogram corresponding to the truncated Polya tree, where you would have where you go only up to the leaves of this magenta tree. Okay, which is equivalent to actually putting all variables down, all y variables down these leaves equal to 1/2. And so let's call it, given TPT T Polya tree prior, given T, you have this this T Polya tree prior, and actually this construction is equivalent, is the same as the optional Polya tree introduced by in the paper by Wong and Ma, except that the authors didn't especially put forward this tree interpretation. Okay, and you have, what's nice also computationally is that you have some form of conjugacy, and you can show that, so given the tree, the posterior is conjugate. That's very easy, it's just like in the usual Polya tree, but remarkably, the posterior in the trees is also again a Galton-Watson, but with parameters that now depend also on the data. And you can get this parameter, it's not really a simple formula, but you can get them recursively by a bottom-up recursion. And this leads to actually fast sampling. And so this has been studied in particular by Lima in subsequent papers and using these fast algorithms. Right, so this computationally feasible. So what kind of results do you get? You can get similar results as in the regression model. You can prove, so that's an ongoing work. So we are, the preprint will soon be available on arXiv. So that's a joint work with Thibault, my PhD student. We get that if you have a alpha Hölder density with alpha between 0 and 1, then you can, you get again the same log square over n to the power alpha over 2 alpha plus 1 in dimension 1 rate for the sup-norm density estimation. Okay, so it means that optional Polya trees are sup-norm adaptive up to a log factor, and this provides a supremum-norm rate theory for the paper of Wong and Ma, where they proved consistency in the supremum-norm of the posterior. Okay, so let me give now a few words in the regression part. I mentioned a little bit the limiting results, and I just mentioned in passing that behind this fixed confidence, at least in the asymptotics confidence band, there was this certain limiting result. So more formally, in this type of multi-scale space, you can show that the posterior, once properly recentered, converges to and rescaled by square root of n, because we have seen it's 1 over square root of n tight, to a certain Gaussian process. Here's a Gaussian noise. And once you have this result, what's nice is that you can use a continuous mapping to get limiting results for functionals that are continuous. If you take any continuous functional from this M space to another space, you can apply continuous mapping. So for instance, you can look at, if you want a band for the cumulative distribution function here in the density estimation, you can deduce from the previous result a Donsker type theorem for optional Polya trees, namely that if you take the empirical CDF, square root n f minus the CDF converges in distribution to a P f0 Brownian bridge. So P0 here is just P f0. Right, and this result tells you that if you take a confidence band centered around Fn, around the empirical, and with radius built such that you get a posterior quantile at level 1 minus gamma, then this credible band has credibility, as confidence, sorry, asymptotically 1 minus gamma. So you get a frequentist justification of this band, and it's also can show that it has the optimal radius in a certain efficient sense. Okay, now let me talk about a slightly different subject. So we have talked quite a bit about the supremum-norm, because we wanted to get results about uncertainty quantifications, about bands. Now let me go back to maybe slightly more weaker L2 type risks to talk about a difference between single trees and forests, and namely a property that that you can get via forests, namely smoothing. So suppose you want to estimate alpha Hölder function. Let's suppose you are in the white noise model, and suppose you want to use a histogram. So the easiest thing you can think of is you just split your unit intervals in capital K pieces, and you just take a regular histogram estimator, and on each piece you just average the data. So here is just maybe slightly fancy formulation. It's just but if you don't know the white noise model, but if in fixed design regression, it's just you just average the observations that you get on the interval ik. Okay, so that's the simplest estimator you can think of. Of course, you have to choose k. If you look at the bias variance trade-off, you get a square bias, which is at most of, so which is bounded by this k to the minus 2 alpha inf1. So the inf1 comes from the fact that you look at histograms, and you cannot do better for many functions because you have some limitations of using a histogram in terms of approximation. And the variance is k over n. Okay, so the implication is that you will get the minimax rate only if alpha is more than 1. So here what's essential is that you have some sort of independence between the heights, and maybe if you get strongly correlated heights, you could perhaps do better. And there is a very interesting, a beautiful result by Sylvain Arlot and Robin Genuer, who considered what they call a purely random forest model for regression. And what they considered is so you just have your regression model on the unit interval, and you take a single tree estimator, and then you shift your on a regular dyadic partition, and then you shift your partition many times. For instance, according to a uniform random uniform variable, so sampled many times, and then you aggregate. And if you do that, it turns out that at least on the interior for any fixed epsilon, on the interior of 0, 1, so on epsilon 1 and minus epsilon, you can achieve smoothness adaptation up to the order 2 and not 1 anymore. Although the resulting aggregation of trees is still a histogram estimator, right? And the idea behind that is that when you do this uniform shift of the regular partition, you get something which in the infinite forest limits looks like a triangle kernel, which is of order 2, and it's then well known that if you use a triangle kernel, you can get optimality up to order 2, at least using the frequentist kernel estimator. And then there is a follow-up paper also by Mortada and co-authors on this. And note also that this aggregation doesn't seem to improve beyond order 2. And then the natural question is, can we do something similar, or what happens for Bayesian forests? So we have seen, let's consider density. We'll look at density estimation, and to avoid these boundary effects that will be present, let us for now consider the case where you are on the torus. So the torus is just 0, 1, but you identify 0 and 1. And then if you have a smooth function on the torus, it just means that it's 1 periodic, and you want also the smoothness to loop well, to connect well between 1 and 0. Okay. So consider the space of alpha Euler functions on the torus. Then we'll use an idea that has been used actually already in practice for Polya trees, is the idea of trying to shift the partition. So if you shift this dyadic partition, say here up to depth 2, just on 4 bits, if you shift it by a random number u, or by a fixed number u, then you get the random partition which is on down with the b0, which kind of loops on the other side, right? So the idea will be to take a Polya tree, a fixed Polya tree, a single tree estimate, and then to shift it by some quantities and see what happens. So here we are going to look actually in the aggregation, we will look for simplicity into deterministic shifts. But we think that that's a work in progress by Thibault, that we can also do random shifts. So the aggregation operation is very simple. So this A script is just you aggregate shifted. So if F is a certain histogram on a regular partition, you shift it and aggregate and then renormalize by the number of trees. So if F is a histogram, then the A of F is a forest, so it's an aggregation, and you can actually iterate this operation also a number of steps, like m steps, and then we get what we call DPA, so discrete Polya aggregate prior, which is the one I described before. So you start with a single tree prior, so with single tree histogram sampled from a Polya tree, truncated at depth L. So here we actually just take the flat tree. You could also possibly take something more fancy like what we were doing before, but let's just take the simple flat tree truncated at L, and then let's apply this aggregation operation, this A to the M. And we can note that in the infinite forest limit, when Q goes to infinity, we actually go to a convolution. So hence this idea of smoothing. So if you do that, yes. Sorry,
yeah, just to let you know that you have 8 minutes before the end.
Okay, thanks a lot. I'll try to wrap up in 2 or 3 minutes. So the result is then that if you take this DPA prior, so recall that so the first parameter is the depth up to which you go. The second one is the number of trees in the forest at one aggregation operation, and this is the last parameter is the number of times you do this aggregation. So if you choose this ln well, in terms of alpha, and note that here alpha is completely arbitrary, then you get the optimal rate up to log factor for the density estimation in density, so in density estimation, so for any, regardless of alpha, strictly positive, with histograms. And of course, the trick here is that the samples, both in the prior and the posterior, are very correlated. And you contract for any possible alpha. So here, this result is for alpha given, but you can also get analogous results in the adaptive case just by sampling the L at random, according to some prior. We can make also an analogy of this result with deep learning. So if you take a deep neural network with a rectified linear unit activation function, you get a very not very smooth object as an output, but at least it's Lipschitz. But there is this very nice paper by Johannes Schmidt-Hieber where he shows that then you get optimal rates up to logs for any regularities alpha, although your learner is only Lipschitz. And here you get a similar phenomenon, but even with histograms. Okay. All right. So just to conclude, this, if you are interested, the Thibaut is talking about it in the contributed session 18 tomorrow. You'll talk about also further results. You can actually remove this torus condition and by slightly modifying the prior. And here is a little picture of this smoothing effect I don't have much time to explain it, but you can see that compared to a truncated Polya tree, you get a much smoother curve in the forest example. Okay, so to wrap up, maybe some key message from this talk is the fact that trees, BART and many of the such algorithms are flexible enough to get sup-norm and multi-scale adaptation. This has implications in terms of uncertainty quantifications if you want to get confidence bands. Tree priors are somewhat in between sieve priors or maybe kernels and spike and slab, where you have a completely free arbitrary sparsity pattern. You have some extra flexibility also of random choice basis, although we didn't talk much about it in this talk. And also another message is that you can have some smoothing effect using forests. All right, and I mentioned already some work in progress. So let me thank you very much for your attention, and hopefully there is a bit of time left for questions.
Thank you very much, Ismaël. So we have time for a few questions, and I'm going to read the first that's been posted on the Q&A by Ryan Giordano, who asks that whether, given that it can be difficult for posterior samplers to mix effectively in tree-based models, can you share your perspective on any gap between your consistency results and practical applications?
Okay, so thank you very much for the question. So the main goal of this work was to give some theoretical guarantees for practically used algorithms like BART or maybe also forest. And of course, it doesn't say that it's super simple to sample in, for instance, high dimensions. It may become more complicated. So I would say that this is, in a sense, a validation results saying that there is a potential in trees to do sup-norm adaptation. And there is a lot of work to be done in better understanding, as I was mentioning. So Judith also asked a similar question about in higher dimensions, for instance, there will be a trade-off between what type of sparsity do you have or do you believe there is in your signal, and depending on it, using a tree method may be very advantageous. But of course, here I'm not so. At least in small dimensions, there are these polynomial time algorithms that I mentioned based on this, for instance, density estimation, the OPT. You can do some, you can still go up to some dimension, to some dimensions. So you can see some recent works by Lima, but of course it doesn't give a general answer on how you sample from tree posteriors or forest posteriors in general.
Thank you. Any other questions? So I had a question, and I think you mentioned it, but then I missed it. So in your forest results, how many trees do you have to add? Like, is it increasing with n or?
Yes, of course. Yes, it has to. So here the number of trees is of this order. So it's of the order of the standard cutoff to the power alpha for one smoothing operation. So this is the number of trees in the first forest, say, and then you aggregate, you repeat this aggregation operation floor A alpha times.
I see.
Right.
And so here you were talking about L2 loss, because I guess the subnorm is super complicated, but
well, we have some partial results on the subnorm for that. But using slightly different approach. So not using exactly this, but it's more complicated indeed. Yeah. But what did you? So you did. Sorry, you didn't finish your question.
Yeah, well, I guess it's probably what you had in mind is that I imagine that to get a subnorm result, instead of the sort of flat tree you're considering, you would need something rather like the optional trees for each of the trees or something like that. Or yeah,
indeed, it can be indeed, absolutely. So here we already wanted to see whether. Because I had also been wondering about the Polya tree and how you can you get something for smoother functions, and this is a way to go to do some aggregation of Polya trees. That may not be the only way, but so that was the goal here. But then you can try to indeed to do more stronger norms, for instance, and that's one of them.
So there are 3 more minutes until the end of the session, I'm told. So is there any other questions from the audience? So I have one last question, probably going to be cut in the middle. So if you add trees, apparently, so this forest story allows you to get more smoothness, better, so reach beyond alpha equals 1. Another way to go beyond smoothness is to go through splines. So you, instead of having piecewise constants, you get polynomial, like piecewise polynomials, and then you smooth out. And do you think there's a chance that the techniques that have been raised, so of course you're losing this conditional independence in this case, can be extended towards these spline stories?
So I think maybe this is a question for Thibaut's talk tomorrow, but it turns out that I didn't pronounce the word, but that's a very good point. In fact, so maybe in this slide, this is actually very related to splines, and what you get is actually, so in the infinite forest limits, the reason actually why you get smoothness to, so adaptation to arbitrary smoothness, is because you have a link to splines. So, and depending on the order of averaging here in this forest, so how much you iterate this forest, this aggregation operation, it will give you a spline of order m, actually, or m plus 1. So that there is a behind. So that's studied in Thibaut's paper. He has also what is called a CPA, I think, prior, where it's a continuous limit in the infinite forest, and then you have really an explicit link to splines.
Oh, but nice, yeah.
Right. So the idea was to try to really stay within the histograms without going to the limit, but it turns out that in fact in the limit you get this spline story in the background.
So then you could directly go to the spline. So with your results, in a sense.
So in a sense, it's also why you can get the result for any alpha and not limited to, and are not limited to 2.
I see. Mm-hmm. Nice. Mm. Okay, thank you very much. So because we have 1 more minute, so thanks Ismaël for a very nice talk. And see you soon.
Thank you all.